Okay, so this week we're going to take a look at section 2.4, which is all about graphing sine and cosine functions. So the transformations that we're going to draw, there's four of them. Okay, four basic transformations. You can take any one of these graphs, sine or cosine. You can shift them left or right. It's a horizontal shift, which we're going to do today. You can shift it vertically, up or down. That's the second one. You can take and stretch it up or down, or you can stretch it left or right. Okay? So those are all four transformations we're going to do. Most of the problems we do are only going to have one transformation at a time in the problem. You could do a problem with all four, but in this class we generally don't. And the first thing to recognize about these two functions is they are not linear. Okay, when we draw them, they're what we call a periodic function. And periodic functions have repetition in them. Okay, we start to get values that repeat themselves over and over. So what happens is you're going to go through all these different y values, and eventually you're going to get back to the y value you started at, and they're going to repeat again. Okay, so all the y values repeat themselves over a certain interval. Okay, and one way to kind of visualize it is to think of the unit circle. Okay, if you draw your unit circle, how many degrees do we have to go all the way around the circle before we end up back where we started? 360. Okay? And that's when things start to repeat again. Right? So if we start here, this x value is 1, 0. So the y value starts off at 0. It goes up, and the highest the y value ever hits is 1. Okay? And then after 1, it starts to come back down. Okay? It comes back down, and then right here it hits 0. When x is negative 1, y hits 0. But then it keeps dropping. Okay? And then the lowest the y value will ever get is right there. That's at negative 1. And then it starts to go back up again. Okay, and this last part goes back up. And the y value then goes back to 0, and it keeps repeating. So the y value will then go back up to 1, back down to 0, negative 1, back to 0. And the interval over which it does that is 360 degrees. So every 360 degrees, these y values start over again. Okay, the length of that interval, okay, before the y values start to repeat, is called the period of the function. So the period you can think of as the amount of time or the number of degrees you have to go through before the function starts to repeat itself. Both your basic sine and cosine function have the same period. Okay? We're not going to talk about changing the period until Thursday. Okay, so from now until Thursday, every single function we graph, it takes 360 degrees for it to go through all its values and start over again. Okay, we said it was 360 degrees, but if you're going to do it in radians, it's 2 pi radians. Okay, this week, all the graphing that we do will be in radians. Okay, so we won't be using degrees this week. So I already kind of said this, but if you graph y equals sine of x, after you get to 2 pi, the graph is just going to repeat what it already did again. Okay, and let me graph a portion of sine, just so you can kind of see this repeating pattern. So I'm going to graph the function sine of x. Okay, I'm graphing it in the negative x-axis and positive. And basically, this section, you know what? I'm going to go like this. Let's do this. Okay. When it starts here, it goes up, it goes down, comes back up. That's one section of sine. That's called one period. Okay. The next section is basically just going to be this one repeated. Okay, so if I just made a copy of it and put it right there, that's the next section. Okay. Now, bless you. In red, we're looking at two sections. Okay, that part right there, that's two sections of the sine wave. Generally, when I have you graph it, we're just going to do one section. Okay? But I want you to keep in mind that it does go on forever in each direction. Never stops. And it always will have this wave pattern. We can transform it. Okay, a couple different ways I already mentioned. We could take and shift it to the left or the right, okay, a little bit. We could take and shift it up or down. That's another transformation. We could stretch it, okay, up and down. Might look something like that. That's a vertical stretch. And we can also stretch or compress it left to right. Okay, that would be a horizontal compression. Okay, each one of those transformations, with the exception of shifting it up and down, has a certain effect on what it would sound like if this was a note and we were listening to it. And we'll tie that in a little bit. So another name for a period, it's also called cycle, and this term is used in other fields. Specifically measuring something in what's called cycles per second. Anybody in a shop where they know what that measures? Cycles per second? No? That's from electrical. Anybody in electrical? Yeah? Not familiar with cycles per second? Nope. Okay, every wall outlet in the U.S. and other countries, it's different, has to operate at a certain frequency. There's a voltage it has to operate at, which is generally how much? What's your voltage of one of these outlets? 120. Okay, 120 volt. Sometimes if you have like an electric dryer at home, that's a 240. That's different. But the voltage, we're not talking about voltage. We're talking about the frequency. Okay, this is alternating current. Okay, in your house. Different from the kind of electricity in your car. That's direct current. Alternating current alternates. Okay, and there's a certain number of times it has to alternate per second. Do you know what that number is? In the US, it's 60. Okay, alternating current runs at 60 cycles per second. If it didn't, you'd plug something in and it wouldn't work right. So if you have a generator at your house or anything like that, sometimes you notice like if you run a motor off of a generator, it doesn't quite sound the same as when it's running off power from the street. And that's because generators don't always have it exactly at 60. Sometimes they're a little off. All right? It could be like 57, 58, and it makes it sound a little different. So if you're used to hearing it, you know what it sounds like. But a lot of times, instead of labeling it as cycles per second, they use the word hertz. Is that what you're going to say? Yeah, hertz. Okay, 60 hertz is the frequency that all alternating current outlets run at in the United States, pretty much. If you go to Europe or other countries, you try to plug something in, that's not always true. So you got to be careful, and sometimes you need like an adapter. Okay? But that's basically how fast the electricity is alternating per second. So if you were to graph it, it might look something like this. It would do that 60 times in 1 second, alternating current. Okay. Generally, we won't be using the term cycles per second. We're going to stick with period. That's what we'll call it, period. Okay, to transform one of these graphs, okay, to find out what the new graph would be, generally we need 5 points. Okay, that gives us enough points that we can sketch pretty accurately our curve. So for a sine wave, here are the 5 key points we like to try to find. Where it starts and stops, okay, in the middle, and that'll generally give us our 3 x-intercepts, and then find the highest point and the lowest point. So for every graph we do this week, that's pretty much what we're going to do. We're going to find 5 points. Okay, if you do less than 5 points, you can't really get a good sketch of the curve. You could do more than 5 points, okay, if you want more detail, but you don't really need it for this. Okay, and these are what I'm going to call the 5 key points, or the 5 important points. And notice here I'm just sketching one period. Okay, that's all that you're going to sketch, just one period. Okay, for each transformation that we do of sine and cosine, we have to know where it starts. If we don't know where the graph starts, then we can't figure out where it's going to go to. Right, so we're always going to start with these original tables. Okay, we'll have one for sine and one for cosine. So if we want to have 5 points that are equally spaced from 0 to 360 degrees, how often would I need to have them? I'm going to do it in radians, but can anybody tell me in degrees? How far apart are these green points going to be, their x values? They have to be spaced equally. And we're starting at 0, and we're ending at 360. Yeah, they're every 90 degrees, exactly. Okay, so we're going to start out with these original tables, spacing our x values every 90 degrees. That's 0, 90, 180, 270, and 360. Okay, except we're doing it in radians. And now to figure out the y values, okay, all we have to do is really draw our unit circle. It's all going to be nice numbers. Okay, we're not going to have any fractions or roots. It's all going to be zeros, positives, and negative ones. 0, 90, 180, 270. I'll write it in degrees just so it's a little easier to see on the circle. And what was sine? Is sine my x value of a coordinate or my y value?
Y.
Yeah, it's the y value. Okay? So when we start at 0 degrees, the y value is also at 0. When we go to 90, well, Sarah, what's the y value go to there? 1. Okay, so we got 0, we got 1. When we go to pi, the y value goes back to 0. When we're at 3 pi over 2, or 270, the y value hits its lowest at negative 1. And then 360, or 2 pi, well, that's a repeat of 0. So the first point and the last points, those are repeats of each other. Okay, so these are the original 5 points of the sine function that'll help you to graph it before you do any transformations. Okay, these are kind of your starting points. Now we get the same thing for cosine. Okay, but now when we do cosine, we're not looking at the y value of the coordinate. If we were doing unit circle trig, we'd be looking at the x value of the coordinate. So when we're at 0 degrees, x is at positive 1. When we're at 90 degrees, x is back at 0. Okay, when we go to 180, we've gone left 1. So that's a negative 1 for x. when we're at 270, okay, we're back on the y-axis, which means my x value is 0. And then when I go all the way around again, I'm back to the right one, so my x value is 1. So these are the 5 coordinates that you're going to use when you're graphing cosine. If you mix up the tables, then you'll mix up which function is graphed when. Okay, so make sure you have table on the left for sine, table on the right for cosine. Okay, any questions on those 2 starting tables? If you look up these points, you can find them all on that chart I gave you last week. Okay, that chart has a lot more too. It has like 30 and 60. And you could graph those points if you want to get more detail and a better curve. But these 5 are enough. Okay, and then we just draw the curve the best we can. Okay, so after you have your original table, next you have to determine where did those 5 points move to when I transformed it. Did they move up? Did they move down? Okay, how did they move? So every transformation that I give you, okay, this isn't true in general, but for the problems I give you it will be, I'm only going to change one thing. I might move it up or down. So if you move something up or down, which axis does that move it on, the x or the y? Moves it on the y, up and down. It's vertical. So that would mean all the x's would stay the same. If all I do is move something up and down, the x's aren't going to change. If I move something left or right, what's changing this time? The x's. Okay? And everything else would stay the same. So if I just move something left, it won't affect the y values at all. Okay? Left and right affects the x values. Okay, so for every transformation, either the x's are going to stay the same or the y's are going to stay the same. One or the other. And whichever one stays the same, well, the other ones are going to change. And it's the same idea if I do a vertical stretch or a horizontal stretch. If I stretch something vertically, that's going to affect the y values because it's going to stretch it up and down. The x's wouldn't change at all. If I decide to stretch or compress something horizontally, stretching left and right, those are your x values. All right, so let me show you some different examples. Okay, with this thing. Okay, so this is one example of what we can use sine and cosine waves for. It's visualizing sound. Sound is not normally something you visualize. You hear it, right? So this picture is created by a device. Anybody know the device that does that? Takes something you hear, makes it into a picture? Yeah?
Oscilloscope?
Yeah, an oscilloscope. Okay? This isn't a real oscilloscope. I need a microphone to do that. But basically what this is it shows you a picture of a certain frequency. Right? And there's different ways I can transform it. So I could take, and the one we're going to do today is when you slide it left or right. And we'll hear what that would sound like. Another thing we can do is we can compress it vertically. That would affect the y values. Or we can stretch it vertically. Okay, that would also affect the y values. Okay, we can also compress it, okay, horizontally, and we can stretch it horizontally. Each one of those things I just did would have a different effect on the sound. The only one that I can't do here is push it up or down. Okay, that was the vertical. Can't shift it up or shift it down. That really has no effect on the sound. All right, so that's one example, and we're going to talk a lot more about that. Okay, another example of where you might see these kind of waves is if you take a look at what's called the electromagnetic spectrum. So basically, your electromagnetic spectrum covers all these different kinds of energies, okay, all the way down from radio waves, okay, then getting a little bit shorter, microwaves, infrared. Also, as you start heading to the right, what happens is the wavelength, or the distance between, say, that peak and that peak, it starts to get shorter and shorter. As it gets shorter and shorter, it gets more and more harmful to us. Okay? In general, radio waves aren't really that dangerous. Okay? Microwaves, you don't really need to do anything special. You know, you can use your microwave and you're fine. But when you start to get into like ultraviolet and X-rays, now you do need to do special precautions to be careful. Okay? So like with an X-ray, does anybody know what they do like at the dentist office when you get an X-ray?
Something like that heavy coat thingy on you or whatever.
Yeah.
Like when they X-ray your mouth, you have to stand in front of the machine and have like a little coat thingy.
Yeah, they put that heavy thing on you, and it's heavy because it's usually made. Anybody know what makes it so heavy? Yeah, lead. Because lead is it's the right kind of composition that it can block things like X-rays. Okay, but we can get beyond X-rays, even shorter and shorter wavelengths. Kind of think of them, the shorter they are, the easier they can get through things. Well, gamma rays are even shorter, and lead wouldn't stop those. There really isn't a way to stop those. But luckily, we don't really have many of those on Earth. Okay, they're mostly in like outer space. Certainly, if you had like a nuclear disaster, you might get some kind of radiation that's released. But that's usually why nuclear reactors are surrounded by like 30 feet thick of concrete. And that helps to, kind of contain it. All right? But these are pictures of what electromagnetic waves would look like. The only part of this spectrum that we can see is right there, the visible part. Okay? So this is about the order of wavelength in meters that we can see. Okay? Anything beyond that, and we can't really see. Infrared, that's more heat. We don't see it, but we can feel it. And then some of these we can't even really see or feel, like X-rays. You don't feel them when they hit you. Okay? But again, it kind of looks like a sine wave. We're not going to study as much about electromagnetic waves. But you can see some of the wavelengths. I mean, they get pretty big when you're talking about like from peak to peak here, for radio waves. These wavelengths are buildings long. They're huge waves. And then we get all the way down to something, with infrared. The wavelengths are as small as like the point of a needle, but that's not even nearly as small as they can get. Okay, they get really small. Okay, so if you haven't studied that in physics, you might at some point. All right, so that's kind of the background about periodic functions. Okay, and a couple quick applications. We're going to look at the one called a phase shift. Okay, so a phase shift is when you translate the graph left or right. And one thing we need to be able to do is when you look at an equation, you have to know which of the four types it is. For today, that's not an issue because you only know one type. Okay? But on the test, you're going to have all four types of problems mixed together. And first thing you got to figure out is what is happening to this graph. Is it moving left and right? Is it stretching? Okay, what's happening? Then once you can identify what kind of transformation it is, I'm going to give you steps for each one. Okay, this is how you know if what you're graphing is a phase shift. So the equation will look something like this. Y equals your function, could be sine or cosine, either one. And then in the parentheses, you don't just have x anymore, but you have x plus or minus a number. When you plus or minus a number inside the parentheses, that's what's going to cause the graph to move left and right. Okay, and what I want to do is take a look at that, maybe not with the sine function, but with a simpler function, like a parabola. Okay, we'll graph x squared, and then we'll graph x plus 2. And we'll try to take a guess which way we think it's going to move, plus 2, if it would move it left or if it would move it right. So here's our basic parabola. Oops. I might have to change my screen a little bit to see it better. That looks good. Okay, now I'm going to try graphing this. I'm going to put something inside the parentheses. I want to take a guess what's going to happen. What do you think the plus 2 is going to do? Is it going to move it left or is it going to move it right? It's going to move it to the right? All right, let's take a look and see what happens. Which way did it move it? Left. It did. It moved it left. Okay, so out of the 4 transformations, there's 2 that kind of work the way you would expect, kind of common sense. And then there's 2 that do the opposite of what you would expect. This is one of them that does the opposite. Okay, when you put in, I know I'm doing it with a parabola, but exactly the same idea is going to apply here. If you put a plus inside, that's going to move it left. Okay, what about if I did a, let's do a minus. Which way is that going to move? Right. Yeah, minus is going to move it to the right. So there's your parabola shifted to the right. So whether it's positive or negative, that controls which way it goes. The number controls how much. So it's not really too complicated. Here are the 2 rules. So if you have x minus a value, that's going to shift your graph to the right. By how much? Well, it depends on the value. If you have x plus a value, it's going to shift every point to the left. Somehow on your reference sheet or somewhere, you've got to try to keep track of which transformations move which directions. When we start talking about shifting up and down, it's more of a common sense thing. Plus is up, minus is down. But people always switch it thinking, oh, it switched with this one, so it probably switches with all of them. No. Okay, this is one that you just have to be careful with, and I'll tell you the other one when we do it. It's not going to be today, though. So minus is going to shift right, plus shifts left. Okay, any question on that idea? Generally, the values that we shift by, okay, it's going to be a certain amount of degrees. How much of a phase shift are we going to do? A 90-degree phase shift? Okay. 180-degree phase shift? Any thought what would happen if you did a 360-degree phase shift? Yeah, it would look the same. If you shift so far that you've gone all the way to 360, you can't see the difference between the 2. And sound-wise, we wouldn't hear a difference either. Sound the same. Okay, so we're going to shift by pretty standard amounts, either a 45-degree shift, a 90, or a 180. Those are the shifts we'll do. Could you shift it by 33.6 degrees? Sure. It's just that's not a very common shift that you would do. Okay, so we're going to start with that original table of values. And then we're going to have to determine what's changing here. Okay, if we're going to shift this thing left or right, which values are going to change? My x's or my y's?
X's.
Yeah, my x's are going to change. All my y's are going to stay the same. So first thing you can do is copy down all the y's from that original table that I just gave you. because they're not changing. It's the x's that are going to change. Okay, and the way that you find the new x's is you have to determine, look inside the parentheses, and look at what has been either added or subtracted to x. Right, so let's say we had a problem. We might end up doing one like this later on. Sine of x plus pi. First of all, it's a phase shift. How do I know? I'm adding a number inside parentheses. So if I wanted to find where the x's would shift for this one, I'd look at what's been added or subtracted. In this case, I've added pi. And because phase shift does the opposite of what you would think, I would subtract pi from all the original x values. Okay, that's the part you have to remember. So you look at what's been added or subtracted, and then you do the opposite of that to each of the x values. Again, why do you do the opposite? That's what I showed you on the graphing calculator. That's just the way phase shift works. You've got to do the opposite. Okay, and that's pretty much it for the explanation. So we'll just do maybe 3 examples or so, and I'll show you kind of what I'm going to look for in an example, and then how I'm going to grade it on the test. Okay, there's going to be 2 parts to it. First, I'm going to look for a table, then I'm going to look for a picture. Okay, does everybody have the 2 steps? Okay. So here's my first problem. Y equals sine of x minus pi over 2. What I've done to make it a little bit easier is I've copied down the original table that I had like 4 slides ago. So there's my original x's and my original y's. Our goal is going to be to figure out a table of values for this function. Okay, first thing I got to figure out is if that is a phase shift. Okay, is that a phase shift? Well, Ben? Yep, how do you know?
Just has the white to turn off your out.
Can you help them out?
X is subtracted by a number.
Yeah, we're adding or subtracting something to x. That would be completely different if I did something like this. That's a very different problem. Okay? This time, you're taking the sine of x, and then you're adding 2 after. Now it's more like the problem we're doing now. Okay. So we just have to be careful where we're adding or subtracting it. In this case, it's inside parentheses. Okay, so since it's a phase shift, what values are going to stay the same? Yep, my y values. This is going to move left and right. It's not going to affect anything up or down. So keep all your y values the same. Basically, what I do on the test is I give 1 point for each part of the coordinate that you get right. So there would be 5 points right there for that problem, just by copying down the right column. The only way you can get this part wrong is if you copy down the wrong column, or you use the cosine function on accident. So we had 2 original tables. You got to make sure you use the one for sine, not cosine. Okay, so we got our y values. Now we need to find our x values. What am I going to do to each of my original x's? Yeah, I'm going to add pi over 2. So I look at what's been done, and I'm going to do the opposite of it. Okay, so I'm going to do 0, plus pi over 2. Pi over 2 plus pi over 2. Pi plus pi over 2. 3 pi over 2. Plus pi over 2. And 2 pi plus pi over 2. Now, all that I really care about is what you write in this table for this part. This is the calculation, but I'm going to be grading your final answer. Okay, so let's start with the first one. Okay, 0 plus pi over 2. Naisha, what's 0 plus pi over 2? Just pi over 2. We'll be keeping every answer as a fraction with pi in it. We won't be using any decimals here. Okay, Lydia, what's pi over 2 plus pi over 2? Okay, think of it, pretend it was just a number. What if you had 1 over 2 plus 1 over 2? What would be the denominator in your answer? 2, yeah, denominator always stays the same, right? That never changes. Okay? We might be able to reduce this, and now what do you do with the numbers in the numerator? Yeah, you just add them. Okay? So in this case, you get 2 over 2, or just 1. All right? So let's go back to this one. So I'll start with a denominator of, it's going to be a denominator of 2. And if you add pi plus pi, how many pi's is that? 2 pi. So what we get is 2 pi over 2. But if I can reduce it, I will. And that just becomes pi. The 2's cancel. Okay, let's look at the next one. Michaela, what's the denominator on pi here? It's 1. There is no denominator right now, so we can always assume it's a 1. Now, if we're going to add these together, we need a common denominator. Okay, Sean, what's my common denominator between 1 and 2?
1, possibly? I don't know.
So, common denominator, we got to find a number that we can use to add these fractions together. So I guess another way to think of it is the smallest multiple that 1 and 2 both have in common.
Wouldn't that be 1?
2 times, you can't do 2 times anything and get 1. Unless you start using fractions. So we're
2?
sticking, yeah, 2. Okay, the common denominator is 2. All right, so Zach, what would I multiply the bottom by to make it a 2?
By 2.
By 2? And what would I multiply the top by?
2.
By 2. Okay, now we have now it's 2 pi over 2 plus 1 pi over 2. Adam, what's 2 pi over 2 plus 1 pi over 2?
Is it 3 pi over 2?
Yep, 3 pi over 2. Good. Okay, next one already has a common denominator of 2. Olivia, what's 3 pi over 2 plus 1 pi over 2?
4 pi over 2.
Yep, it would be 4 pi over 2. And what would that reduce to?
2 pi.
Good, 2 pi. 2 pi is, we would always reduce it as much as we can. And then the last one, we don't have a common denominator. So Ashley, what's my common denominator again?
2.
2. So multiply the bottom by 2. Multiply the top by 2. So now we have 4 pi over 2 plus 1 pi over 2. And Iris, what is that?
5 pi over 2.
Good, 5 pi over 2. Okay, once we get faster with the arithmetic, the problem isn't really that bad. Okay. Now, if you look at the final answers, you don't see a pattern. You got pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Okay, but let me read everything with a denominator of 2. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. The next one would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, and so on. Since we're only graphing one period, we're only doing 5 points. But you could keep going once you see the pattern. Okay, any question on the table? All right, so 1 point for each x and y value that you get correct. So this table right here would be worth 10 points. Now we need to graph it. The graph, once you have the table, that part's easy. And the graph itself, I'm going to make worth 2 points. Okay, but what we want to do is label our x-axis with those values. Don't label your x-axis 1, 2, 3, 4, 5. Okay, that's not going to work very well. So we got pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. If you were doing this in degrees, basically you'd have 0, 90, 180, 270, 360, 450. Just going up by 90s. Now for your y-axis, that's fine to use 1 and -1. And now graph the points in the table on the graph. So pi over 2, we're at 0. Pi, we're at 1. 3 pi over 2, back to 0. 2 pi, we're at -1. 5 pi over 2, back to 0. Okay, when you sketch it, try to make it look like a somewhat smooth curve. There are no sharp turns in this graph, so it shouldn't be pointy. It should all be somewhat curved. And there's your graph of y equals sine of x minus pi over 2. Okay, the original would have been right about there. It would have gone from 0 to 2 pi. Now it's been shifted to the right. Okay, any questions on that? That's a phase shift. All right, so we did one with sine. Let's try one with cosine. Okay, this time I don't have the original table there. So if we're not sure what that is, that's probably the first thing we should find. Because without that original table, you can't do anything. Okay, Ethan, can you give me my x values in the original table for cosine?
0.
Yep.
Pi over 2. Pi, 3 pi over 2. And 2 pi.
Yep. Happen to be the same x values as sine too. Okay, now the y values are important. These are different. Okay, how about Sam? What are my y values in the original cosine table?
1, 0, 0.
Yep. So with cosine, it starts at 1. That's at its highest. It comes down to 0, keeps going down to its lowest value, -1, and then it starts to head back up. And it always ends where it starts. All right, so now we know what the original values are. Now we can make a table for cosine x plus pi. Now I know today this question doesn't make as much sense, but first we have to figure out the type. It is a phase shift. It's the only one we know. And with a phase shift, we have to figure out what stays the same. Okay, so Max, what's going to stay the same when we do a phase shift?
The
So which way is a phase shift going to move the graph?
left or
Left and right. Which axis goes left and right?
X.
So if we're moving left and right,
Oh, it's going to Y.
the y's are the ones that are going to stay the same. We're going to move left and right. So x's change, y's stay the same. 1, 0, -1, 0, 1. Okay, now I need to get my new x's. Okay, Paige, how do I get my new x's? What do I do? Add pi to what? Add pi to the original x's. Okay, does everyone agree with that? Add pi?
Always give it the opposite.
Yeah, you got to do the opposite. Remember, with phase shift, that's the one you got to do the opposite. There are some transformations where you won't do the opposite, but this one you do. Yeah, we're going to subtract pi. So we've got 0 minus pi. Pi over 2 minus pi. Pi minus pi. 3 pi over 2 minus pi. And 2 pi minus pi. Okay, so remember, no decimals when we do it. Just leave everything as a fraction. Okay, and inside that box, those will be my final answers. Okay, Ben, what's 0 minus pi?
Negative pi.
Yep, negative pi. And now we can keep going, finding common denominators till we see a pattern. But once we see the pattern, we can just use that. Okay, we don't see a pattern yet. There's only one number there. So Josh, what's my common denominator between 2 and 1? 2. What would you multiply this 1 by to make it a 2? Yep. So double what's in the bottom, double what's in the top. So now we have pi over 2, take away 2 pi over 2. Matt, what's pi over 2, take away 2 pi over 2?
Negative pi over 2.
Yep, negative pi over 2. Pi minus pi is 0. And if you write everything with a denominator of 2, you'll see the pattern. The first x value is negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, and what would the last one be? 2 pi over 2. And the next one would be 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. The numerator is going up by 1 each time. If you don't see the pattern, that's fine. Just do your common denominator. 3 pi over 2, take away 2 pi over 2. There's your 1 pi over 2. Okay. So there's our table. 1 point for each x and y value to get correct. And now our graph. All right, so let's label it negative pi. Each one is going to be basically 90 degrees apart. So it's negative 180, negative 90, 0, positive 90, positive 180. Okay. If something is going by ones, you don't need to label that. I'm going to assume every problem that if you don't label your axes, you're going by ones. Because in Algebra 1, that's what you do most of the time. Go by ones. If you want to go by something other than ones, you need to label your axis. A lot of people lose a point on the test for not labeling their axis. I'm not going to label my y-axis because I'm going by ones on it. Okay, so negative pi, we're at 1, 0, negative 1, 0, back to 1. Now the cosine, it's a little trickier to sketch. Remember, it's still part of a curve. So don't draw it as an absolute value, which is like a V shape. Sometimes what I do is kind of look at what would lead up to it. And if it kept going, it would be something like that. Okay, so try not to make it, like a pointed V, because it's really not. It's part of this wave. Okay, so that's a phase shift of cosine. And we went to the left. Okay, any questions on that one? All right, so we did a shift by pi, which is 180. The first problem we did was a shift by pi over 2. That was a smaller shift. It was only 90. And then for our last shift, this one's even smaller. We're only shifting by 45 degrees. Or in radians, pi over 4. Right, so let's try this one together. We'll finish this one up, and then I'll play a phase shift for you. I'll let you hear the sound, the best we can kind of do in this room. All right. Who can tell me what's the very first thing you need to start off with? Before you can even really start doing the problem. Sarah?
Graph the original. Sine.
Okay, you don't have to actually draw it, but you need the table for it.
Yeah, that's fine then.
Yeah, we just need to write down that table. In the homework, what I am going to have you do, though, is draw the original, draw the new one, so you can actually see it move. Okay? On this one, I didn't draw the original, but the original would be more like this. Should have used a different color, but it's been shifted to the left. Okay. I'll have you draw the original and the new one on separate graphs so it doesn't look confusing. Okay, let's get our original values. Okay, how about Tom? Can you give me my original x values for sine x? Yep, starts out at 0. Good. Pi over 2. And last one? 2 pi. Good. Okay, you can't really mess up the x values if you mix up the tables because they're the same, but the y values you can. All right, so Emily, what are my y values for the original sine table?
0, 1, 0,
In the last one?
0.
0, yep. So sine starts at the origin, goes up to its maximum, then starts to come back down, keeps going down to its minimum, and then back to 0. All right, now we can use that table. Let's get our new table. Okay, step 1, determine if that's a phase shift. It is. Okay. Step 2, figure out what column stays the same when you do a phase shift and copy that column down. Okay, so Shelby, what column stays the same?
Y.
Yep, Y's. Okay, so copy down my y values. Now I need my new x values. Okay, Amy, what am I going to do to all my old x values to get my new ones? So always do the opposite of what you see in the function. So in this case, it's going to be added. We're going to add pi over 4. Pi over 2 plus pi over 4. Pi plus pi over 4. 3 pi over 2 plus pi over 4, and 2 pi plus pi over 4. This is one, it's kind of helpful to see the pattern so we don't have to keep finding denominators of 4. Okay, first one's pretty straightforward, pi over 4. Okay, next one, how about Naisha? What's my common denominator between 2 and 4? 2? How would you make the denominator of 2 into a 4? What would you multiply it by? 2. So we're going to double the bottom, double the top. So we have 2 pi over 4 plus 1 pi over 4. That's 3 pi over 4. Does anybody have a guess what the next x value will be? Yeah?
5 pi over 4?
Yeah, it will be 5 pi over 4. Numerator is going up by 2 each time. If you're not sure, find a common denominator. In that case, it would be multiplying top and bottom by 4. And there's your 5 pi over 4. Okay, what about my next x value? 7 pi over 4. Again, I'd have to double the top, double the bottom. It would be 6 pi over 4 plus 1 pi over 4 is 7 pi. And the last one, 9 pi over 4. Okay, those are my x values. questions on those x values? Okay, so now we want to set up our axes and graph it. Okay. Pi over 4 is a little bit tricky to set up. Okay. So pi over 4 is 45 degrees. So if you did something like this, pi over 4, and then you put 3 pi over 4 next to it, that's not right. Okay, we can't do it that way. Because what you're saying here is this is 45, this is 135, this is 0. So you're saying between here and here is 45 degrees. Then you're saying between here and here there's 90. Well, that's not consistent. All right. So there's a couple ways we can do it. One, you can treat what's in the middle as the pi over 4s. Okay, that's one way to do it. Or we'd have to leave a larger gap for the first one. Okay. What I'm going to do is I'm just going to label between the marks. Okay. So this would be pi over 4. And then the mark would actually be 90. But 135 is halfway between 90 and 180. Okay, it's right in the middle. So anytime you have a pi over 4, this is one way you can set it up. Okay, 3 pi over 4 is 135. The next mark here would represent 180. The next one would represent 270. We're right in the middle. We're at 225. Okay. And if you convert 5 pi over 4 to degrees, you'll see what it is. It's 225. Okay, and so on. Just keep setting them up. 7 pi over 4 and 9 pi over 4. Okay, any question on setting up my axes that way? Okay, now we can graph it just fine. So pi over 4, we're at 0. 3 pi over 4, 1. Back to 0. Negative 1. Back to 0. So pi over 4 is a very small shift. You're only shifting at 45 degrees to the right. That's pretty small. Okay, tomorrow we can also talk about other ways you can set up these axes. But for this problem, that's how I would do it. All right, so let's take a look at, or let's listen to what that would sound like. Okay, the easiest way to explain kind of what a phase shift would sound like is first just looking at that example. Okay. If I could do it perfectly on 180, you could see exactly what I'm talking about. But let's pretend those are exactly 180 degrees out of phase. So we've got two ways. One in red, the other one in blue. And what's going to happen when they're 180 degrees out of phase, okay, is they're going to combine together and make a new graph. And let's see how they would combine. Okay. Let's start with where that point would go. Okay, that point has a height of 0 on the red and a height of 0 on the blue. So if you combine two things that have a height of 0, what would you get?
0.
Yeah, this point doesn't move. It stays right there. This point is also going to stay right there. And this point basically stays right there. Okay, the next one. Okay, let's look at this point and combine it with this point. What's the highest that the graph of sine goes? 1. And it's at its highest right at that point. What's the lowest that it goes? -1. And if we combine the heights of those 2 points together, what do you get? You get 0. And now it's reversed here. The blue wave has a height of 1. The red wave has a height of -1. We combine them. We get a height of what? 0. And that happens at every point. All these heights are going to combine to 0. So what does that mean in terms of a sound?
They cancel each other out.
Yeah, they cancel each other out. And if I play it, I have to line it up just right. It's hard to get it exactly perfect, but if you can get it exactly perfect, those 2 waves would cancel each other out. As they start to come back in phase again, right, they start to get louder, but it's not because we're changing the volume, it's because we're changing the phase. And really, the way you have to demonstrate it is with 2 speakers. Okay, and you could do this, well, I guess in your car if you just use the 2, like try just the 2 front speakers, or 2 back, either way. If you're sitting at certain points in the car, and you can somehow generate a frequency and change the phase of it, it will sound at a different volume depending on where you sit in the car. Right? If you had them exactly out of phase and was sitting right in the middle, the sound wouldn't completely go away because it's going to echo off the car roof and the walls and the windows, but it would sound softer. And then as you move away from the center of your car towards like the driver or passenger seat, it would start to sound louder. So it would actually sound different volumes in different parts of the car. Right? So that's kind of a cool thing to do. If you can get a wide open space outside, it works much better. And put 2 speakers, say, 50 feet apart and play with the phase. You get really interesting results.
What else can you make it do?
What's that?
What else can you make it do?
Well, with a phase shift, that's all.
Oh.
So phase shift isn't, it's not overly interesting. To us, we perceive it as a change in volume, but it's because the waves cancel out.
What if you like move it up and down, does that change the...
We'll talk about what stretching it up and down would do tomorrow. And we'll talk about something a little more interesting than that on Thursday. Okay, so the homework tonight will be the worksheet on phase shift. Okay, so let me pass that on.